Good evening. How was everyone tonight? Hopefully everyone is doing well. All right, well, we're going to get back into it. I had a question about when the exam was. So good evening. The first exam will be due on the 30th. And what I'm going to do is it'll be basically an assignment set, but it'll be bigger. It'll just be a greater one. We'll see how that goes for you guys, and hopefully that goes good for everybody. So we'll see. Yeah, it's not exactly the way I wanted it. Well, okay. So just experimenting with some different things here. All right, so recall, where were we at? Oh, that's right. We were talking about Boolean algebra. And so what I want to do is I want to do at least one more example. Here, let's get my drawing tool out. So let's try this one. X, Y complement, we should talk a short second about order of precedence. So I haven't really talked about it yet, but when we look at this, which one comes first? An and or an or? And the answer to this is an and comes first. But usually what we're going to want to do is we're going to want to put parentheses around things to make it very clear which gets done first. And that's the reason why we're going to do that. So, all right, so I'm going to look at this and I see, aha, look at this. The whole thing is negated. Let's try using De Morgan's rule, or De Morgan's law, I'm sorry. De Morgan's law. And we're going to split it. We're going to say this part right here is the second part right here. And this is the first part right here. Okay, so I'm going to take the first part as is. Except for I need to negate that. So I do this, put parentheses around that, and negate it. And then I'm going to, this was an and between them, but now we're going to switch that to an or. And then everything in here stays the same, X or Z, except for we have to negate that. And then we have to negate the whole thing on the outside, which then turns it off. So then it becomes positive, so we don't have to negate it anymore. All right, can we simplify it from here? Yes. Well, notice that this first term is in, I don't like the way that looks here. Let's make this smaller. Fine tune eraser. Get in here and get rid of that. It looks a little cleaner. All right, we notice that this first part here also has this negation on the outside. And so let's go ahead and do a De Morgan's law on that. And we also see at the same time, independently, this also is has a complement on the outside. So we're going to go ahead and use De Morgan's law on that as well. Okay, so this will be first part. This will be the second part. And then over here, we'll have first part and the second part. Okay, so we say X complement or Y. Go ahead and put that in parentheses. This doesn't change. That just drops right on down. And then so then we distribute this. So then we go X complement, and this was an Or, so let's turn it into an and. So let's put them right next to each other. And that's a z, so let's make that a complement. And then we take the complement on the off the outside of that. And we can put this in parentheses as well. Now, can we go any farther? And it looks like maybe, right, because we've got this x complement in both sides here, but it turns out that we can't pull it out, right? So if we tried to get it out of here, I mean, we could, right? We'd put it on the outside here, but then if we did this one on the outside, it would be like, it would be 1 plus y. No, because we can't take it out of this term, this half of the term. So we couldn't do that. So we're just stuck. That's our simplification. That's De Morgan's law twice. So let's try another one. Y complement plus x z x complement, and we're going to take the complement of that whole thing, so we're just going to take the opposite of that. Alright, so in the same way, we're going to see this first part here. That's the first part, there's the second part. Okay. So, first part, y complement or x, and we're going to complement that. And then this was an and, so we're going to change it to an or. And then we're going to take this, z, x, complement, complement. Then we notice here, both of these, right? This one is got the complement on the outside, so let's go ahead and pull that out. There's the first part, there's the second part. We can do the same thing at the same time on this part here. All right, so let's try that. All right, so then we go, the complement of y complement is just simply y. And it was under an or, but we're going to change it to an and. X complement. And then we complement the outside and it goes away. This, we didn't mess with this, we just did the two halves. So then we have z or z complement or x double complement, which is just x. And then we could put parentheses around that like this if we wanted to. But we don't necessarily need to, because the ors won't matter which order that get done in. We actually have an identity that helps us with that. Can we simplify this anymore? No, we cannot, because we can't pull any of these out. So that gives us a negation for this one. How is this useful? Well, this is useful if you have an if statement that you can identify. So sometimes it's easy to identify when something shouldn't happen, not when something should happen. So, like, I want this event. I don't want to talk about events. The player's turn is over as long as they don't pass go, right? Or pass a certain space on the board. It's over if they don't. Oh wait, no. Let me back that up, because that's the wrong way to say it. They'll continue playing until they get past a certain space on the board. So it's still their turn, and they're going to continue repeating. So we can think of that, maybe that's a while loop. And but we have a not in there, right? When we don't get to something, when we get past something, or like if we don't get past something, we're going to continue on. So we could use De Morgan's law to negate that and switch it around. Although in that case it probably wouldn't matter because it's in the negative form, but it's usually better to put it in a positive form. People tend to think easier on the positive side than on the negative side. All right, so that's a couple examples. Okay, so let's. Oh, I suppose I have to put in my bottom so that this actually works. Oh yeah, I can use my scroll wheel. Okay. All right, so back here, squiggly line. Okay. Let's just do a truth table. Let me just make a truth table. Put my mouse out here. 3 parts: X, Y, and Z. Let's go ahead and get some lines in here. We're going to use F to denote the function. Okay. So we do your regular 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. It's 1, 2, 3, 4, 5, 6, 7, 8. Looks like I got them all. Okay. So let's define this function. So when all of them are zeros, then we're going to go ahead and set this to be on. And then that'll be off. And then I'll go on again. And then off again. And then on again. And then off again. And then the last two, let's go ahead and put as being on. Okay. So what I want to do here, this is a truth table for our function. Now, I don't know what our function looks like in Boolean algebra, but sometimes this is what I have, is I know what the behavior is, but I don't know how to really represent it. And so what I can do here is I'm going to look only at the ones, and I'm going to write them down in AND format for each term. And then I'm going to OR each of them up. Let me show you how this works. So I notice here that where's my mouse at? Keep losing it. Okay. So the first one is right there. And that is when they're all false. So that would be X complement, Y complement, Z complement. So we can AND all 3 of those together because all must be true, or in this case all must be false. That's why we put the complement on them. And then we're going to go ahead and do an OR for the next part. So we can skip over the one that's false because we don't care when it's false. We only care when it's true. And so then we see here, we see X complement, a Y, and a Z complement. So X complement, a Y, and a Z complement. Then I do another one. That is X, Y complement, Z complement. Do another one. X, Y, Z complement. And finally one more. X, Y, and Z. Hopefully that doesn't run off the screen for you guys. Yeah, it looks like it's going to be pretty close. Okay, so I suppose I could pull it over, but that's all right. Okay. I could look at simplifying this. This is called a product of sums. Product of sums. Now, I could come in here and start doing some work on this to try to simplify it, right? Because I see in these first two terms, there's an x complement and z complement, right? So I could say, all right, well, let's go x complement, z complement, and then inside we'd have a y complement or y. And how does that help us out? Right, because this turns into a 1. It's always true. That was something we talked about last week. And I could do a similar thing here, pulling the x and the y out and leaving the z in the middle. All right, well, let's go ahead and do that then. So then I get an x, y complement, z complement, and then x, z, no, x, y, I had it right the first time, z complement or z, again, that disappears and turns into a 1. So I could say x complement, z complement, or x, y complement, z complement, or x, y. No, I can do the same thing here. I can't do the same thing here, can I? I could pull the z out, but that doesn't necessarily help me because I don't get negations. I could, because I can reorder this, so I could put these two next to each other. X complement, z complement, plus x, y. No, because I still am not being able to pull anything out there, am I? Nope. Might be able to pull a z complement of both of these two, but then that doesn't get us an identity on the inside of the parentheses. So I think this is probably as far as we want to go. We'll call it good. Sometimes you want to mess around with it and kind of look at it in different ways. And you might try to do a De Morgan's on it. I think a De Morgan's will just make it worse. All right. But we can use this same truth table to talk about, oh, well, let's do a different one. All right. So x, y, z, plus y complement z, plus x, y, plus x complement y, plus x, z. Yuck, right? Well, yeah. But we can do some work. So let's get to work here. First, let's go ahead and distribute this through here. Well, I guess it doesn't matter. Let's pull the y out, because there are y in both of these two terms. We can say xy, z plus z prime, or z complement. Now let's look at this here. We can pull a y out. We still have this over here. y, x or x complement plus x z. And again, see, we can take this and turn it into a 1, take this and turn it into a 1. So we have xy or y or xz. Can we do anything to make that better? We could try pulling these y's out, right? Because we know that there's under and, so it would be 1 and y, but then that doesn't really help us out any. We could try pulling this x out of the y and the z. It might make it a little easier to read, right? X or y plus c plus y. Makes it a little easier to read, but that isn't necessarily any better either. So we'll call this one done. Although some people would argue, right, that's 5 character, this is only 4, so maybe this is better. But then we added in the parentheses, so who knows? Okay. All right. All right, let's look at another kind of thing. So we had our first 3, right, which was and, or, and not, right, complement. So I'm going to talk about 3 new ones, and they're like the secondary grouping. And the first one is XOR. So this one's XOR. X, Y, X, XOR, Y. And one way to say this, we call it XOR, and we'll even say it XOR, but it really means exclusive OR. Well, let's look at the numbers. It says one of these must be true, but not both. So this goes 0, 1, 1, 0. And this is really just a combination of others. I can actually write this as a combination of the original. So this is X or Y negated with X and Y negated. That's at least one way to do it. I could probably do a De Morgan's. I know I can do a De Morgan than this. X naught, Y naught. Oh, no. I jumped too early on that side. Bigger. X or Y. And since all I did is I took this value here and I just took that the opposite of the negation of that. And then here, I'm going to do the same thing here. I'm going to go X or Y. X and Y with the complement on there. I could do it again on this side. Let's try doing it this side. X or Y or X not or Y not. I made a mistake. Maybe I didn't do this right. X or Y yeah, this isn't correct. Oh, you know what we should do? We should use a tool we just got, right? The product of sums. Let's do the product of sums on this. We're only looking at ones that are true. So we've got X not Y or X Y not. Yep. That is the product of sums for this, right? Because this first part is the negation of X and then Y, and this one is X and the negation of Y. Okay, good deal. All right, so yeah, that's weird. There, that might help me. All right, so that's XOR. Let's just grab this. Grab this here. And move it over here. Put it down there. Okay. Let's do the next one. Not and. X. Y. Oops. X. And. So this would be not and. 0, 0, 0, 1, 1, 0, and 1, 1. So not and is the opposite of and. So it's 1, 1, 1, 0. So not both of them. One of the two only. And we could do, again, we can do the product of sums. Oh, I need that on there. And then we can go X not and Y and what am I? Oh, X Y negation. And we'll notice here we can simplify this one a little bit because we can pull out these X naughts or X complements, and then the Y, these two here are going to cancel each other out, right? So we're just going to have not X or X. Why not? Grab that part. Pull that over a little bit. So just give myself a little bit more room. Because there's one more. Nor. This one is not or. X nor y, 0, 0, 0, 1, 1, 0, and 1, 1. All right, so nor says not or. So it's the opposite of or, which is 1, 0, 0, 0. So this one, it would be simple, right? This one is simply x not, y not, and y not. It has to be that way. That's the only way we can do it, because that's the product of the sums, because there's only one true value here. Okay. Some of you will have noticed, maybe, that we have several different combinations here in this line, because, right, we have the or, which is 3 1s and a 0, and the and, which is 3 zeros and a 1. So that's 5. There are 8 different possible permutations. So, and we haven't done all of them, right? So, is it 8? No, I'm sorry. There are 16 different possible permutations. And they're all defined. These are the most common ones. We can build we can build these. We'll show you how to build these in a different way here in a minute. Okay. Actually, let's talk about actually, what do I got here? I can do that. Hey, look at that. I like that. That's nice. Okay. So we can talk about something called Karnaugh maps. Or sometimes called just a K-map. What this does is, instead of doing a truth table like this, we're going to do the truth table a little bit differently. And last week, I did some things with that crosshatch like that. But it's not a truth table. So this is a definition table, but it's not a truth table. So let's go back up here and let's grab, I'm gonna grab this right here. Oops. I'm gonna grab this. Let's go ahead and copy that. Come down here. Let's see, can we paste that in? We can. That's not exactly what I wanted to do. There we go. Grab the whole thing. And then pull that up to where I want it. Okay. So I'm going to draw this a little differently. Instead, I'm going to have the X over here, and the Y and the Z on top. So this will be 0, this will be 1. And then I'll go 0, 0, 0, 1, 1, 0, and 1, 1. Those are my four different possibilities of Y and Z together. Okay, so then let's go here. When we've got 0, 0, 0, 0, that's a 1, right? We've got a 0, 0, 1, that's a 0. A 0 with a 1, 0, that one is a 1. And then a 0 with a 1, 1, That is a 0. And I come down here and I go 1 with double zeros. That's a 1. And then a 1 with the 0, 1 is a 0. And then my last two here are both 1s. So, all right, so this is how the Karnaugh or the K-map works. What I'm looking for is groupings like this. This isn't a great example. Or this one. Because it allows me to reduce terms. So I look at this one and I say, well, what's the same in both of these two places? The only thing that changes is the x. So the y and the z are the same, but the x can change. So we can just say y, z. So now we've covered those up. So now let's look at this one. And we can say, oh no, these should be not. They should be complements on both of those. And this one here, we go this direction. We see that this y, z naught, and then x, right, changes. And then here, x is a 1 always, y is a 1 always, but z changes. So then we say plus x, y. So let's go ahead and look at that. Let's go up here and see what we got there. Let's bring this down so we can compare it. Copy. Come on down here and paste that right on in there. I'm going to grab it a second time. I can pull it over here. Okay. Well, that's the same, right? That's the same as this. Huh. It's interesting, isn't it? Didn't come out the same. Well, we doubled up on this x here. Did we do this one right? The x and the z out. That's right. Or x naught, y naught. Yep, that stayed the same. And then this one here, we pulled the x and the y out, left the z naught, z in there. Okay, yeah, that's right. And oh, we just reordered it. Okay. These two are equivalent. Oh boy, I thought that would come out nicer than that. It did not. Well, there you go. We could do a truth table. That's a thing you could do. So that'd be interesting. Do the truth tables on these and see if they actually do come out properly. Well, I could take a z out of these, right? Or z prime, I guess. Out of these two. And I could do it out of these two as well. interesting. Oh, right, but it wouldn't give me an identity on the inside. Well, I'm not going to dwell on it. This is another way to do it. We did double up on this one, but it turns out that it doesn't matter, because if it's true twice, it's still just only true. So there's no such thing, right? You can't. That's probably where we ended up going wrong there, or why we've got that It's not really necessarily a mistake, but it's in there because this one's in there twice. If instead we did this last one here was as an X, Y, and a Z, then we could probably form that into the other one. But we don't need to do that, because regardless of what the value is Z is, we know that this will be true. Okay. One of the other things we can do with a Karnaugh map, actually, let me, yeah, let's just kind of get some more space here. Because we're going to use it. So let me do the same thing here, except for I'm going to change this algorithm just a little bit, just so I can show you another thing that we can do. X is 0 and 1. And then up here we have a YZ, so 0, 0, 0, 1, 1, 0, and 1, 1. Okay. So we can do this, but then what we're going to do is I'm going to put 4 of them together like that. I'm going to put these 2 in here like that. So now we only have 2 groups. We have this one, but we also have this one. So what stays the same and what changes here? So if we look at this one's easy, right? Because that's the same as we did before. So we say that that's, oops, Y complement, Z complement. All right, so what stays the same? Y is always the same. X changes, Z changes. Y is always the same. The other ones change. And because there's only 2 possibilities in those permutations, there's 4 possibilities of those permutations, and we've got 4 there. So one of the things with these is if we do a square like that, each dimension must either be 1, 2, 4, 8, 16. It has to be a power of 2. So in this case, right, this is legal because it's 2 by 2. This is legal because it's 2 by 1. And a 1 by 1 would also be legal, although we don't need one here. So that's a Karnaugh map. And these can be really useful because it allows you to get to something, in this case, right, that's quite simple, that if we did a product of sums, we would have had 6 sums, and it would have taken us a long time and a whole page at least of paper just to reduce that down to this, if we could get it there in a reasonable time. And it's possible we couldn't. So that's why Karnaugh maps can be really useful. And we'll talk about that as well. Now, when I'm gonna transfer all of these over into gates, into logic gates. Okay, so let's go over the basics. OR goes like this. We want to make sure we have a curved back. We say this one is X and this one is Y. We have a curved back, and then we want to kind of bring this out to a bit of a point. That's the OR gate. And it functions exactly the same way as we would expect before with the algebra, with the Boolean algebra, right? So this is like saying this. All right, so here's the AND gate. This one has a flat back and then a semicircle for the front. Mine are always probably too flat. You can make that more of a dome if you want. And this is the same as saying X and Y. All right, so then you might ask, oh, how about the NOT? Yes, we need to do a NOT, but that only has one thing going in. And that is flat-backed, and then a triangle. And it's important to put this little circle right there. That completes our NOT. So that's like saying X or complement. That's NOT, the opposite of X. All right, now let's look at those three new ones we have. XOR. So it looks exactly like this, kind of. Actually, the book doesn't bring this out to a point, but that's okay. It makes it rounded. That's fine. The important part is the back. This one has a double line in the back. I like to do points on mine. Notice there's a double line there. And this is how we write this. It's like a 0 with a plus symbol in it. Exclusive OR. And it's exactly the same as an AND gate with the circle out front. Does that have a... Then we have a NOR gate. Curved back. I do the point because I think it makes it cleaner, but I guess that's just the way I learned it. And that is X or Y complement or NOR. we can we can actually use oh yeah, okay, that makes some sense. All right. So remember I told you that there was 3 basics, right? An or, an and a not. It turns out that we only need 2 of them. We need the not gate, and we need one of these 2. We can use the other one to create the first one. Trying to remember how to do that. There is a way to do it, though. If I use this one, yeah, okay. Let's just use AND gates. Gets a little tricky. We have an X and a Y. They're going to come in at the beginning. At any point, I can branch them like this, but I want to make sure I put a dot there, a black dot, to denote that I'm branching them, not just going over the top of it. I can pass that through this. Do the same thing with this one. This gives me both a complement and the correct version. Okay, so I could do product of sums, but that's not what I need to do. Oh, okay. Right, because I can use De Morgan's rule on this one. So that's tantamount of what I'm going to do. So right, so if I had X or Y, that would be the same as, oops, X not Y not. Oh, quantity not. That's De Morgan's. So let me start over on this then. Because I don't need to do that break. That's nice to know, and we might use that in the future. But right now we're not going to use it. Because what we need to do is get the not of both X and Y, or the negation of both of them. Then bring it up here, pass this through an AND gate, and then through a NOT gate. So that is oh, that's weird. It's not quite getting it. all the way to the edge of that box. All right. We need to see a truth table on that? Or does everyone buy that this is correct? That this is really just an OR gate? Let's do a truth table on it. All right, so first off, well, let's just look to see, does this properly what I'm doing here? Right, so the last thing is the not here, that represents this right here. So I can strip that away, and then I'm going to and the not of both of them. So that actually does, that's accurately done there. Okay, let's do X and Y. So this line here is X prime, and this is Y prime, and this is X prime, Y prime. All right, so one, one. All right, so then we have X prime and Y prime. And then we're going to have to do X prime, Y prime. And then finally, we're going to do X prime, Y prime, or complement. All right, so negation of X, 1, 1, 0, 0. Negation of Y, 1, 0, 1, 0. These two ANDed together, we get 1, 0, 0, 0. We take that value and negate it, we get 0, 1, 1, 1. X or Y, 0, 1, 1, 0. So these two values are equivalent to each other, and this is an OR gate made with an AND gate only. I could use De Morgan's law the other direction and eliminate the OR gate and just make it an AND gate, or to eliminate the AND gate and make it an OR gate. Internally, as far as circuits go, everything is an AND. Everything is an AND when we actually break it all the way down to the circuits. Which means this right here is internally what an OR gate looks like. And we'll talk about some more complicated ones as we go here. All right, let me think. What's the next topic here? Oh yeah, there's a lot more. Oh, that's an interesting one. Don't care conditions. All right, let's go back up here, and I want to grab this again. I'm going to build a sum of products on this truth table. All right, copy that again. One down here. I just like that green. That looks nice. Oh wait, we can use purple instead, huh? There we go. Not deep purple, but it's purple, so we'll keep it. All right, so need a little bit more space here. All right, let's go ahead and paste that in. Hey, look at that. It came in right exactly where I wanted it. Okay. Where is my... There it is. Okay. All right. So we're going to have our x coming in. Our y coming in. And our z coming in. So we're going to go ahead and put these on here like this and go ahead and put a knot on that. Just makes life a little easier. Let's do the same thing here. And the same thing down here. Okay, so this first one is the complement of x, the complement of y, and the complement of z. So, okay. Also, we can have 3-part ones. So, let me draw that here, and then we'll I don't know. Hopefully, I'm gonna have enough room there. Maybe. So we can actually have 3 parts like this on an and, like x, y, and z. And what we can say is this is just x and y and z. And we just put them all together like that, and that's actually proper. It's perfectly fine. It's really 2, and then the output from that one goes into the third one, or goes into a second AND gate, really. But it doesn't really matter. We can just say that's fine. We can do the same thing with OR gates. X, Y, Z. That's the same as saying X or Y or Z. Okay. Oh, actually, if I need more room, I can just do this. All right, perfect. Okay. So let's take these negation ones here. Let's bring this up here, and then we'll bring this one up there as well. And then we're going to bring this one up as well. Oops. Bring that up here. All right, that represents our first one. Then we look at our second one. We see the same thing for x, so let's go ahead and break that off. But y, we want this one. And z, come off of here. I like to keep them all in the same line, but this is pretty close. I could have extended that straight out and that would have helped me. But, okay, then the next one is x. I'm going to bring that down. And then not y. And, oh, let me just branch it off right here. Not z, not z. There's my 3 coming in. So that's 3 of them. Okay, the next one will be x. Y. And not z. Oh, just go from here. Then the last one will be X, Y, and Z. So now that we've got these, let's bring these together. And then bring these together. And that is a gate that represents our truth table. That looks pretty complicated, doesn't it? Well, maybe we should have thought about simplifying it before we got started. There's a lot of different ways to do these things. There's a lot of different ways to understand truth tables like this and interpret them. And sometimes the gate system will actually work to your advantage and you'll be able to kind of have insights in it. Sometimes the Carnot maps will work better. Sometimes Boolean algebra will work better. And it just depends on how you decide to go about trying to solve the problem. And so that's one of the things that this class actually really excels in, is its different ways of thinking about problems. Which is why I'm stressing process so much. But because there's so many different ways, we have to have a little bit of practice with each one so we get a sense of how they're going to work, or how we can transform the problem into that. Right? So if we want to do a gate problem, we have to figure out how to transform whatever we're looking at into a gate problem. And so that's something I'll leave to you guys to try to work out, but that is an important part of why this class is important. Not only do we look at the binary stuff, but we look at the gates and things like that, but we also will. Right, we introduce some different ways of thinking about the problem. And we can approach, like in this case, right, we did a gate for this truth table. We go up here, we did a Carnot map for this truth table, that's right here. And we already know this is different. This is different than what happened when we did a product of sums. It's different, it's completely different. Well, not completely different, but it was partially different. So, and then, yeah, that was it. Okay, so, and that's important because there's three different ways to think about the problem. How do we represent this? Now, this isn't in code yet either, right? It's just different ways of thinking about these problems. What's the next one? The next one is don't care conditions. That's an interesting problem. And I think we will try to pick that up, I think, next time. So sometimes in a function, we can actually say, we can say, I don't care. I don't even want to consider that one. So, I could look in a truth table here and I could say, well, this one is a question mark. It doesn't matter. So you can include it if you want, but you cannot include it. It's not possible for it to happen. So we will not see it. And so that's an important note as well. Oh, that's an interesting one. Oh, that would be an interesting one. I was just thinking about doing one here that instead of outputting, in this case, right, this output's either on or off. But how about if we had different gates here that fired all the different 10 digits, right, 0 through 9. And then we looked at, right, this one 0, 0, 0, that would fire the 0. 0, 0, 1, that would fire the 1. 0, 1, 0, that would fire the 2. Right, so we would go through whatever gates we needed to go through, and then instead of combining them here with an OR gate, we would just simply push this into output of 0. And then the next one we would do is this one, which we didn't represent here, and that would be output of 1. That'd be an interesting abstraction, and maybe we'll talk about that later. But right now, we're not going to talk about that. Anyways, assignment 2 is due Monday at 5, and I will get assignment 1 graded tonight or tomorrow night. So in any case, I'll probably look at it and start it tonight, and then finish it up. So look for those scores and that feedback. Yeah, and so I guess 3 weeks from now we will do that take home. I think what I'm going to do is when we do that one, what I'll do is it will be due at 5 o'clock on a Friday, just like all the rest of the assignments after this week. But I won't publish it till after. I'll have to think about that, how much time you guys get to work on it. I probably will publish it on Wednesday sometime. So you'll get a couple days to work on it. So make sure you're blocking out some time right up at the 30th there. But we won't have the regular lecture that Thursday. We'll skip the lecture that week, or that day. So it'll be as if we took that time to do the in-class test. And you guys will do that at home with whatever notes or book or internet that you want. I like that solution better because I don't have to worry about people using things they're not supposed to. And I don't have to not trust you. I can just not trust you by giving you the exam and writing it in a way that makes it equal and fair for everybody. So that will be the way we're going to do it. At least for the first exam, we'll see how that goes. But this is my first time teaching an online class. I think I talked about that in the first week. So sometimes we'll be experimenting with things and we'll have to shift gears. And if we have to, that's fine. And I'm perfectly willing to do that. But my guess is most of you won't have too much trouble. We'll see. We'll see how we'll cross the bridge when we get there. All right, I think that's it for everything for today. We're going to be done a couple minutes early again, which I don't necessarily have a problem with. An hour and 20 minutes is an awful long time. It's an awful long time to listen to me talking, and it's an awful long time for me to be talking. So with that, I will bid you all a good night and a good weekend. And we will see you again next week on Monday. All right, bye-bye.